Hi guys, I thought I'd just get these recorded for us before the last 2 weeks of term rush away. Second last week of term we're going to look at mutations, and then next week we'll look at evolution. So here's a quick little slideshow on mutations. Now we've talked about this a couple of times, but it's possible to take a karyotype. So to collect a sample from an individual and from it extract the DNA. A bit better than we did. Ours is very much bucket chemistry, but able to extract them and find the 46 chromosome pairs. Now my head appears to be over the top of this diagram. I don't think I can move myself, can I? No. Can I? Nope. Oh, I can move myself. I'll put it up there. And start again. And you can see how we've got 22 pairs, so 44 chromosomes, which we know as autosomal, and then the next chromosome and a Y chromosome. So we know this individual here is male. There are two chromosomes in each pair, so we know there's no obvious abnormalities. There may be others we can't see straight away, but this is one way of getting a sample. The banding tends to respond to dyes to show us parts of the chromosome that are coding and things. And then we have this line here, which is where the centromere, the point that joins these during mitosis, is found. So looking here at what we would call a metacentric centromere, so it's in the middle, it's chromosome number 1 in humans, that's right in the middle there. You can have submetacentric, which are these guys here, so it's not in the middle, it's not at the end, and then we talk about agrocentric when they get towards the end there. So we can sample quite easily, get hold of tissue and do this sort of sampling. We describe pairs of chromosomes as being homologous, so an identical pair, or non-homologous, so the two chromosomes have different information on them. So if you had an allele for blue eyes and an allele for dark eyes, we'd have a non-homologous pair. We'd have different alleles. And we just talked about those ideas here of metacentric, submetacentric, and acrocentric. And you can see how this diagram here tries to show us how here's our chromosome pair, the centromere in the middle, do the P arm above the centromere and the Q arm below the centromere, and it's made of DNA which has been wrapped around these histones and coiled and folded up into this package. So there's a lot of DNA in each chromosome, which we've talked about a few times now. We've talked about sex determination, so those X and Y chromosomes are those that determine whether an individual is male or female. And in the case of mammals, ourselves, a male is XY and a mother is XX. In some birds and reptiles we find a different system where the father is homologous, so ZZ in this case, and the mother is heterologous, so we have big Z and W, so they're unalike. A different way of describing the same outcome. Then what we're really interested in this particular podcast is the idea of mutations. So for each gene, you would normally have 2 alleles. And so at some point in time in this diagram here of these fruit flies, there's probably only one allele, and that allele is for normal fruit fly development. And there's this particular diagram showing wing development. Over time, that's mutated. And so we have these dichiate wings, we have miniature wings, so they're normal but they're shrunken, have rudimentary wings, so they're sort of there. We have, should we say acute, I thought, cross-veinless cut, so we can, you can't really see the detail on the wing there, but it's slightly different wing to normal. And these vesicle wings, which are of no use at all, they can't fly with these. But each of these has been created by a mutation to an allele, creating a different protein that creates a different shape for the wing. And if they're functional, they hang on. If they're not functional, they don't. And we've talked a few times about how human beings arose in Africa. So it's a species, and normal eye colour is dark, and normal hair colour is dark, and normal skin tone is dark, because that confers enormous advantage for us in what's otherwise a harsh environment, where you get lots of skin cancers and diseases of the eye and things because you haven't got enough pigment. As we moved to the north, into northern Europe, that was a big disadvantage because we need to be able to make vitamin D to take calcium up from our diet and create bones and support our tissues. So being dark-skinned was a disadvantage. So at some point in time, there's a mutation has spontaneously occurred which has created lighter skinned people. They have been more successful. So we'll talk about evolution next, but the idea is that lighter skin gave them an advantage because they could make more vitamin D and survive better in those low light conditions. So mutations can be very, very useful, and of course they can be quite harmful. So we've got some mutations here showing hip dysplasia, cruddy brown bone joint, and these strange toes. I shouldn't say strange because some people in the class might have them, but really quite distinct toes, which is unusual for most people. So we talk about point mutations, and a point mutation is where one single nucleotide, one of those adenine, thymine, guanine, cytosines, if you recall those, is different, has changed. And so they can be produced three different types of outcome. A silent change, so changed the actual nucleotide, but didn't change the amino acid it coded for. So the protein's a protein, doesn't change the protein. They can create a missense, so we've got a change in the amino acid sequence, and we get a different protein. So dark eyes were original, blue eyes are now a recessive trait, it's a recessive allele of dark eyes, and that's probably a missense. We're seeing a new protein that produces a different pigment in the eye. And of course they can produce what's known as nonsense. So the new protein is of absolutely no value whatsoever, this won't work. And that can be quite, can cause death and all sorts of things. But won't get passed on, obviously. So here's a one way this is occurring. We'll talk about a substitution. So my DNA template reads thymine, adenine, cytosine, adenine, thymine, adenine, cytosine, adenine, thymine. And the amino acids that are produced for that are methionine, start of course, tyrosine and valine. But if that allele there, that nucleotide there, changes from A to G, then GTA will give me the amino acid histine. Or something like that. I can't think what his stands for there. But now I've got a different amino acid. So the substitution of one nucleotide has changed that particular amino acid. It may or may not make a change that's useful. It may be totally useless. We don't know. But that change has occurred. We can delete a base. So, let's go back up. Oh, this is my template strand. If I take that C and remove it, so we've still got TAC, ATA, so we've still got methionine, tyrosine. The valine now becomes ATA, because that A goes there, that T goes there, and I'm making up the fact that A must be here, so we get A there, and we get tyrosine again. But the other thing, of course, here is that every amino acid downstream of this point has a potential now to change, and that can make a massive difference in the structure of our protein we make. You can also insert one. So again, here we are at valine, but I've inserted an extra G. So that G goes in there, C goes across to here, A down to there, T starts the next amino acid code, and my valines become arginine. So again, all the way downstream I've got changes in my amino acids. So I've inserted one base, it's changed all the amino acids. So mutations can occur in two places. We talk about germline, so if they occur in the gonads in the making of gametes, sperm and egg, then we see that change being passed on. If I have a mutation, I'm exposed to too much sunlight, and that causes mutations in the DNA of my skin cells, that will cause changes, and may cause skin cancers and things, but I can't pass those on. They're somatic. They're in my body cells. So the ones of most concern to us, for a species point of view, is germline changes. And they can be good changes, they can be bad changes. We exist as different human beings because we have been exposed to germline change. So in fact, we are sitting in a classroom full of mutants. We're all different, and we're all different to whatever normal was when human beings started. So it's possible to detect these changes, and there's lots of ways of doing that. And of course, people like to study these things. We won't go into the details, but biochemistry is quite complex. What sort of things cause mutagens? I think it causes a mutation. So what sort of things are they? Well, fever will cause mutation. So if you've got a really nasty disease and it's causing excessive fevers, then you may well cause mutations. Exposure to radiation, of course, is one of those classic ones, and so the sun's just enough, but X-ray is another one. So of course you go to get an X-ray and they cover you in these lead sheets and run out of the room, take the shot. So they were often concerned about too much radiation for the radiologists and the nurses. And of course carcinogens like nicotine and the drug DDT, which is used to kill insects like mosquitoes, are known to cause mutations also. So the other change, it's not quite a mutation, but the other possible change is when meiosis goes wrong. And we sort of talked about this the other day, but not in any great detail. So polysomy is when we have too many chromosomes. So during mitosis or meiosis, we should see the chromosomes falling apart and going into different gametes, different sex cells, sperm and egg. And if that works properly, we get 46 chromosomes when we put those sperm and egg back together. One of the classic times when it doesn't work is a thing called trisomy 21, which you know, of course, is Down syndrome. And people with an extra 21 chromosome have a whole lot of conditions. We talk about the short stature. You know, Down syndrome people have shorter stature normally. Very poor muscle tone. And you can see with the girl there, the muscle tone in her arms is fairly poor. And often have a delayed intellectual development. There's a range of condition within trisomy 21, but Down syndrome people have certain conditions in common. Interestingly enough, of course, to create Down syndrome, so trisomy 21, there must be monosomy 21. Somewhere along the line, a gamete's going to get together with another gamete, and one of them's not going to carry a 21 at all. They're stillborn, they're miscarried. They actually don't develop at all. So it tells a lot about what's found on chromosome 21. You also have polyploidy, so you get more than 2 sets of chromosomes. It tends not to occur in humans, but very much something you see in insects and plants. Plants particularly have all sorts of strange things with polyploidy and end up with multiple sets of chromosomes without any problems. They just continue to work, which is a bit weird. And there we go. So that is mutation. And I'm all done. If I can find the button that says done.